significant quantum gravity effect. And in particular, this is the standard picture of a gravitational collapse.
Oops. No, just the laser you press only.
Where is it?
In the middle one. See, you turn off this.
I see.
You will come. Just this.
So this is the standard picture of the gravitational collapse. Essentially, in general relativity and apparently reasonable assumption, one can see that collapsing matter lead to the formation of space-time singularities. Then there are two possibilities. The singularity is hidden behind an event horizon, and in this case we have a black hole, or the singularity is not hidden behind an event horizon, and we have a next singularity. Now, in the first case of black hole, in general relativity and in 4 dimension, there is a very nice property, because essentially the only possibility is a curved black hole. Actually, this is a theorem, but there are several versions of this theorem, which some different assumptions, but in the end, the conclusion is that there is only one possibility, and this is a Kerr solution. On the other hand, in the case of naked singularity, and there is no a similar uniqueness theorem, we have infinite possibilities. Here, however, the problem is that space-time with next singularity present several kinds of pathologies. For example, you cannot predict. You lose you cannot predict what happens at the singularity. Typically, there are a region with closed time-like curves. So several kinds of pathologies. People think that these kinds of pathologies are unphysical. So the usual solution is to assume some form of the cosmic censorship conjecture. You say that next singularity cannot be created in our universe, so you exclude this possibility, and eventually so you obtain what it is called the Carter-Israel conjecture. I mean that the collapsing matter lead to formation. The final product of the collapse of matter is a Kerr black hole. This is the standard picture. Kerr black hole. This is just to remind you basic ingredient. It's characterized just by 2 parameters: the mass m and the spin j, or the spin parameter j over m. And the spin parameter cannot exceed the mass. Otherwise, you have a Kerr-Max singularity. However, this picture presents some questionable argument. But from an observational point of view, at present, we don't have any information about the space-time around astrophysical black hole. I mean, we know that there are very compact objects in the universe that are likely to find part of the gravitational collapse, but we don't know if the space-time around them is described by Kerr metric, and we have no evidence that these objects have an event horizon. This is from an experimental observational point of view. As for the theoretical point of view, well, first of all, in general relativity, the cosmic censorship conjecture does not hold. I mean, we know several counterexamples which looks physically reasonable and which violate the cosmic censorship conjecture. I mean, some regular initial data which lead to the formation of space-time singularity. There are several examples in the literature, even if in general it is difficult to say that if these initial data are physically reasonable. So this is somehow an open problem. And however, this final point is that one can argue that the presence of space-time singularity is usually the place where one should expect new physics. And even, for example, even the existence of regions with closed time-like curves, this issue, for example, has been investigated recently by a couple of authors, and in supergravity, where there are some solutions with closed time-like curves, and apparently you cannot rule out the solution. And some authors claim that actually, if you consider other sector of the theory, we can expect that there are no regions with closed time-like curves, because there is the formation of the domain wall, and essentially the region with closed time-like curves is the result of your analytic continuation of a metric across the domain wall. So actually there are no pathologies in the full theory. I mean, this is at least something. But anyway, the idea here is that in a standard picture, you can the final product of a collapse, final product of a gravitational collapse is just a Kepler call. If you relax the cosmic censorship conjecture, you can have space-time with next singularity. So where you actually can expect important significant quantum gravity effect. And if you expect this quantum gravity effect, maybe the theory, the space-time, has no pathologies, and maybe the assumption is of the cosmic censorship trajectory is actually not necessary. It's just it is due to our poor knowledge of the theory at high energy. And so if you consider the possibility that actually you can produce this space-time, actually people often talk about effective next singularity, where actually there are regions outside an event horizon where you can predict what occurs without a theory of quantum gravity. So in this case, you can expect that around this very compact object, quantum gravity effects are not negligible, actually can be important, and you can also expect deviation, some kind of deviation from the Kerr solution. This is the basic idea. And this is just an example. The strongest evidence of existence of black hole is probably the black hole candidate of the galactic center. Here you can study the orbit of individual stars. You fit the data, and eventually you can conclude that at the center there is an object with a mass of about 4 million solar masses and a radius smaller than 45 astronomical units. This is essentially the smallest distance approached by one of these stars, which is still relatively far from the object. I mean, 600 spatial radii. So you cannot really, for example, you have no evidence of the spin of the object. And you can exclude other possibilities like the cluster of some luminous bodies. And eventually you can conclude that the most reasonable possibility is a Kerr black hole, just because, however, because you assume that the final product of the gravitational collapse is a Kerr black hole. However, the situation may change in the near future, and here I would like to talk about the very long baseline interferometry observatories. These are here the picture is not quite clear. Anyway, you have several stations. In each station there are telescopes working at millimeter and something millimeter wavelength. So this is essentially it is a kind of observation based on interferometer technique. A few years ago, the group of Dolmans published a preliminary result. But they used only 3 stations because other stations are under construction. One in Hawaii, one in California, and one in Arizona. And they showed that in the near future, with a larger number of stations, we can obtain a resolution of some supermassive black hole, like the black hole candidate in the Arctic Center, and even of nearby supermassive black hole, with a resolution smaller than the event horizon. And
what are these observatories looking at? What is the signal they are detecting?
I mean, they
On the block.
they look for. They look at the accretion flow around the black hole. Of course, the radiation emitted in the accretion process at very small scale. And here millimeter and sub-millimeter wavelength. And the idea is also to launch some satellite. This is the VSOP, stand for Very Long Baseline Interferometry Space Observatory Project. VSOP-2 should be launched in 2 or 3 years, but to start really to do physics, I mean to test strong gravity, we have to probably to wait for VSOP-3, which will be launched in 12, 15 years maybe. And one of the main targets of this very long baseline interferometry experiment is to observe the shadow of black holes. The shadow is essentially a dark area over a brighter background, and this can be seen when the black hole is surrounded by an optically thin and geometrically thick accretion disk. Essentially, yes, here you observe the accretion flow. And the shape and the position of the shadow is determined by the space-time around the black hole. In particular, it is determined by the photon capture radius. So we can, with this technique, with this observation, essentially we can probe the space-time at 1 to 3 gravitational radii. And the position and the shape and the position of the shadow can also be computed considering a distant observer who fire a photon to the black hole. There are some photons which are absorbed by the black hole and other which come back to infinity. Essentially, you can measure the cross-section. This is actually the determination of this cross-section, and it is more or less essentially the same of the shape of the shadow.
So very much we are looking at the plane of the accretion disk. Is that what it is?
I mean, this is the case of a black hole with spin parameter 0.999, so a fast rotating object. Here the observer is on the equatorial plane. No, here here the observer is on the equatorial plane. That is, the inclination angle is 90 degrees. Here the observer is along the axis of sigma.
But isn't this precisely the direction we should follow jet coming towards us? Accretion disk?
Here I'm considering just a cloud surrounding the object. However, if you consider a jet, the jet should emit dominantly at a shorter wavelength. These are, we are at millimeter and up to sub-millimeter wavelength. And well, here of course you see the shape of the shadow is a cycle for symmetrical reason. On the other hand, this here there is an asymmetry due to the fact that the photon orbit for co-rotating and counter-rotating orbit is here there are two important comments. First of all, a shadow and in general and non-gravitational process does not depend on the gravity theory but only on the metric. And this can be an advantage in comparison with gravitational wave detectors. I mean that in principle, with gravitational wave detectors you can measure very precisely all the parameters of the system. However, you have to know the theory very well, and in particular, I mean not only the metric but also the theory, because the emission gravitational wave depend on the theory. For example, the Kerr metric is a common solution to many theories of quantum gravity, but to predict the exact shape, the exact form of the wave, you have to know the theory. On that, this may be an advantage in the case of this kind of experiment, because you don't need to know the theory, but just to assume something. And the intensity map of a direct linear gravitational flow depends on the accretion process. So this may be a problem. However, the shape and the position of the shadow are not affected by the accretion process. I mean, here the intensity map is different for different accretion processes, but the important ingredient which can be used to test gravity is exactly the shape of the shadow.
But to test classical gravity, I mean,
yes,
not quantum at the moment, because it cannot be quantum, right? I mean,
yes, this is classical gravity. I mean,
but why do you need the interferometer for this? That's what I missed. Why you need an interferometric design for the? I mean, you have 3 simultaneous observations.
You need interferometer. You need to have a good resolution.
To get a good resolution.
And of course, if you consider if you have very large, long distance station, you can improve your resolution. So, with simple possibilities beyond the usual Kerr black hole is superspinor, solution that it was suggested a few years ago by Gimond and Orava. And as a first approximation, superspinor can be modeled as a compact object whose gravitational field is described by the Kerr metric with a spin parameter larger than n. And this is because, well, if you consider some deformation of this object, these are typically smaller. The effects are smaller than the effect of the larger spin parameter. However, the original idea cannot work, because actually you cannot have a very, very compact object which looks like a next singularity, because in that case you expect some instability, in particular the equilibrium instability. So you need an object at least with a radius of at least 1 gravitational radius. And so from this point of view, this object may look like more an exotic stars. these, for example, are some simulation of a shadow. Actually, yeah, I considered some very small rally because at that time we didn't know about the equation instability for this kind of object. And anyway, if you consider a larger radii, you essentially increase this angle. I mean, this somehow this is the case of spin parameter slightly larger than 1, and here this is the case of spin parameter 2, around 2. And essentially, if you consider a larger radius of this object, you increase this angle. And for larger spin parameter, we expect that this triangle is larger, because essentially the counter-rotating photon orbit increase. However, this is not the most important phenomenon in the case of the superspinner, because the accretion process can be quite different, and this can also be investigated by very long baseline interferometry experiment, because they have a good resolution and they can observe the accretion process very close to the object. In particular, in the case of a superspinner, I mean, you can consider the accretion process in the curved background with arbitrary value of a spin parameter, and essentially you find three kinds of accretion. For small value of a spin parameter, you find a black hole-like accretion, I mean standard accretion. Here I consider Bondi accretion. So near the horizon, the accretion is supersonic. As the spin parameter increase, the accretion process becomes less efficient, and in particular, at a certain point, the accretion flow, the accretion is everywhere subsonic. And for a larger value of spin parameter, there are some peculiar features, and in particular, we observe the formation of outflow around the equatorial plane. Here, just the plot, the radial, the plot on the equatorial plane, or radial velocity and the temperature. Essentially, as the spin parameter increase, the radial velocity decrease, and the temperature and the density increase. And at a certain point, only around the equatorial plane, you observe some outflow. These are the plot, but are not very clear in this projector. Anyway, here you should observe some low density region where there are the outflow. I mean, essentially, the matter accretes from the pole, and you observe equatorial outflow.
Excuse me, these things that you're showing are what? Are numerical simulations?
Numerical simulation. Yes, so the accretion process onto this object. I mean, space-time, with, in particular in this case, with spin parameter of...
So you put the background square space-time, it's a fixed
yes.
background space-time,
yes.
and then there is accretion disk. But you have not, it's not taken into account the effect of the accretion on the space-time.
Yes.
Is that correct?
Yes, that's correct. But this is usually is computed energy. For example, in the case of a system belonging to a binary system, I mean a stellar mass black hole with a companion. Usually this is computed energy variable because it is much smaller. The accreting gas is much smaller than the mass of the object, and you don't expect even that any significant evolution of the spin parameter due to accretion, because
right. If you're looking for some exotic object, you should take into account that this is a logical possibility, that you may
I understand that this is what normally happens in the things that you see. But if you're looking for something exotic, you should take into account the possibility that you may be in a situation where this doesn't hold and the accretion is big enough to affect the space-time, and then you don't have a clear space.
But the accreting matter comes from the matter of the companion. The companion is essentially from the wind of the companion, and so you more or less know the physics of the star.
But you're looking for exotic things.
Yes, but the compact object is an exotic object. The gas around the exotic object comes from the companion in X-ray, for example, in X-ray binary system.
You can have in mind that you may find a situation which you declare it to be exotic physics, and all you have is a very, very small black hole with a huge companion that is accreting so much matter that is actually influencing your spacetime. I mean, that's a simpler possibility than saying that you have found something that is exotic.
Just did some other example simulation. I don't have every time. Here, just to summarize the result of flow, I produce flows to a massive object because of repulsive gravitational force in the case of this super spinner. And this is very different. The situation is very different with respect to usual black hole because of the flow are produced by my relatively far from the object. So in the case of very long line interferometry observation, you can have a good resolution to distinguish the two cases. The flow are emitted around the equatorial plane and the accreting matter which we compact the object from the poles. You can expect also a higher accretion luminosity, and yes, and essentially the phenomenon does not depend on the equation of the equation of state of the accreting matter. Yeah. The second possibility I would like to talk about very briefly is a Tomimatsu Sato object, because it is essentially a simple extension of the curve metric. Instead of the mass and the spin, we have the mass, the spin, and the deformation parameter data, which reduce to the curve metric in the case data equal 1. And as I say, you have a deviation from the usual quadrupole moment. The Tomimatsu Sato solution is a regular solution far and in a relatively close to the massive object, but close to the surface of the object there are a lot of pathologies. In particular, you have a ring singularity, which is a curvature singularity, and between the ring singularity and the surface of the object there are regions with closed time-like poles. So in this case you can expect some correction to quantum gravity effect which can solve this pathology. You can repeat the same exercise as in the previous case. You can predict the shape of a shadow. In this case, of course, the correction is smaller because since it corresponds to a higher order correction in the multiple moment expansion of this object. Here I report the relation between the two rally for different angles. Here the same for an object with spin parameter 0.7 and an observer on the equatorial plane. Here the same. A couple of comments just to conclude. The two shadows are quite similar because in the end the direction of the curve metric are at the level of a few percent. Actually, in this case, the idea is that in general relativity, if you assume that there are no next singularity, you have only the Kerr solution. If you relax the cosmic change conjecture, I mean the possibility that there are next singularity, at least in the classical theory, outside the event horizon, you allow for the existence of this next singularity. However, here in this shadow, you don't observe any feature associated to the ring singularity of the Tomimatsu solution because actually the ring singularity is really close to a surface of a massive object, and with this kind of experiment you can probe the space-time at the photon gravtation, photon capture radius. To test the Kerr metric, we need to probe the space-time very close to a massive object because any deviation from the Kerr metric, if any, is very small. And this means in particular that near future ground-based experiment or space mission like BSOP2 will not be able to detect any difference with the Kerr metric, and Tomimatsu object. But with more advanced space mission like BSOP3, which will be launched maybe in 12, 15 years, it is still challenging but not out of reach because it should have a resolution, at least the Tomimatsu solution could be tested for supermassive dipole at the graphic center and for some heavy supermassive dipole in nearby galaxies. And here I conclude. These are just the reference, and that's it.
Thank you very much. It was nice talking for keeping your time perfectly. So we have 10 minutes for questions or comments. Yes.
In your picture of the Kerr black hole, you have the ring and a ball in the middle.
You mean yes?
But when you show the shadow, you only see the shadow of the ring, or where's the ball?
This is the shadow of everything. I mean, if you are an observer, and for example, I mean, and you fire a photon to this object, you don't observe the ring because, but actually, this is not in scale. I mean, the ring singularity is very close to the surface. So, I mean, if you send a photon, there are some photons which are captured by the orbit, by the object, and some photons which are scattered and come back to infinity. If you consider this ideal experiment, you find that this is the cross-section, and indeed you don't observe any feature associated to the ring singularity because...
So what are the two lines? I don't understand that.
Oh, yes, that's right. The black line is the case of the Tomimatsu solution, the data equal to Tomimatsu solution, and the red line is the case of a Kerr black hole with the same spin.
Okay. And the inside is what you don't see, is black.
Yes, inside this cycle is that.
Sabine, you wanted to ask some questions?
Yeah, so what does it have to do with quantum gravity? I mean, is there any chance that if we're lucky we can look at the quantum gravitational region, is that what you're saying? I mean, these are all classical solutions, right?
Yes.
Yeah.
The idea is, I mean, the original idea by Dumont and Dorava was to, that, I mean, that in the case of a Kerr metric, the situation is a little different, and and you can actually you can observe the radiation coming from the very center of the object. But I repeat, the original idea cannot work because the object is unstable. Here, the idea is to consider deviation from the kinetic. I mean, you assume that general relativity is the correct classical theory of gravity, and in this case, you expect some next singularity, some singularity outside the event horizon. You cannot really probe the next singularity with very long baseline interference observation. At least if for some reason, for example, in the case of the Matheson solution, if for certain reason the singularity can emit some is very bright. In that case, you should observe the ring singularity. I mean, for example, in the case of here, the observer is on the equatorial plane. You should observe some bright line here, but yes, otherwise, with a very long baseline interference observation, with the shadow of this object, you cannot observe the next singularity.
Yeah, so maybe, sorry, I have a follow-up question. Maybe it wasn't a little bit fuzzy. I was basically wondering if you thought maybe about something like gravitational lensing. I mean, in a compact objects, with gravitational lensing, you have nothing with the Schwarzschild radius, and you get a particular luminosity curve, stuff like this. So I'm wondering if you have an object that doesn't have a horizon, but it looks different, if this image would look different. You know, it's this kind of moving through the line of sight of some stellar size object. I forget which sort of thing it is, microlensing or...
Well, here, yes, essentially the photon orbit are very similar to the case of the Kerr black hole.
So basically you cannot distinguish whether
yes,
there's really a singularity or whether there's something else that can form gravitation.
Yes,
I mean, at this point. But
it's
it's
very...
kind of what you're aiming at some point? Or?
Yes, I mean, it is... yes, it is I mean, the two shadows are very similar.
Another question? Last one, actually. Yes.
I just had a quick question about the ergosphere. Where exactly is the ergosphere in relation to that ring singularity?
Can you repeat this again?
Where is the ergosphere compared to the ring singularity? Where does it lie?
Is it within that? Is it within the radius of the ring singularity? I mean, because you were mentioning
the ergosphere, for example, in this case, the spin of the object is 0, so there is no ergosphere. In the case of in this case, well, and even for higher value of the spin, yes, for the capture radius, the photon capture radius for rotating orbit, here, it is inside the ergosphere. So the ergosphere is here.
Daniel.
I have a comment. I empathize very much with the idea of looking at the sky and seeing if the objects will affect there. fall in line with what we expect from general relativity. But I'm concerned about these singular solutions, because once we have a singular solution, we know that the theory is unpredictable after that. The Cauchy development stops. So we cannot continue to use the theory to the future of it. I cannot trust the theory to make any predictions of how anything will behave, because I know my equations have broken down. There is no Cauchy development of your data. So, well, perhaps I should end that.
Well, here the idea actually is that, I mean, if you, for example, if you consider a test particle going to approaching the singularity, I can understand that you use predictability.
But you produce predictability not just when you're close to singularity, you produce predictability in all the Cauchy development. So everything that this applies in the future of the singularity is completely unpredictable by our normal theory.
For example, people who consider the ontological space-time next singularity and close time-like course, they say that essentially the prediction of the theory, the metric, is correct up to the domain wall, where there is.
That's where I disagree.
I mean, this is a phenomenological point of view. Of course, if you don't have the correct theory of quantum gravity, you cannot be sure of anything. I agree. But the claim of some people is that essentially the metric of the space-time is correct up to this domain wall, which occur very close to the region with pathologies. And if you follow this idea, that you can essentially consider a space-time, the gravitational field of this object up to a certain radius.
I think we have to cut it here because. So Sabine has an announcement.
I know that a few of you have some trouble with their apartments. So if those of you who are affected could please come to me and give me your name and the apartment number. Okay, so I think we can go for a coffee.
Thank you. So let's.